These will be your notes for Unit 1, Day 3 of Calculus 1. If you would like to see the warm-up, review question, or any homework questions we covered in class today, just take a look at the finished notes in our module. So today we're going to talk about limits some more, and we're going to talk about limits where the x value is approaching infinity or negative infinity, meaning we're going to look at what's happening on the really far right-hand side of the graph as x approaches infinity, or the really far left-hand side of the graph as x approaches negative infinity. Another way of thinking of that is as the end behavior of the graph. We're also going to be looking at limits when the y values that we're getting, the height of the graph, the actual limit, is infinity or negative infinity. So the first thing let's remind ourselves of is end behavior. So what are the tails of the graph doing? So we're going to look at the tails of the graph. So when you first learned about end behavior, you looked at it in terms of function like x squared, where if you just drew in x squared, you have a happy looking parabola. So the end behavior is both tails of the graph are shooting up to infinity and infinity. So we could say the limit as x approaches negative infinity of this function, f of x, well actually we can just say x squared. What's the tail as I'm getting farther and farther to the left-hand side of the graph? That tail is getting higher and higher and higher. So that limit is going to be infinity. You can also say it does not exist because infinity is not a real number, but we're going to put positive infinity to show that it's shooting up. And then the limit of this graph as x approaches positive infinity, that's going to be what's happening on the right-hand side as the x values get larger and larger and larger. What are the y values doing? They're also shooting up. So the limit as x goes to infinity of x squared is also positive infinity, or you can say does not exist. Or we could say y equals negative x squared, and so this would be your sad-looking parabola. And so as x goes to negative infinity, the y values are also going to negative infinity, and as x goes to positive infinity, the y values are going to negative infinity. So the limit as x goes to negative infinity of the opposite of x squared, well, that's happening. What's happening to the tail of the graph as I'm getting farther and farther to the left? That tail is shooting down to negative infinity. And what's happening as my x values are getting bigger and bigger and bigger, so as they're approaching positive infinity, well, those y values are also going down to negative infinity as I'm approaching the right-hand side of the graph. Or we could look at y equals x cubed, and remember from our parent functions, that's the one that looks like a snake. And so as my x values are getting smaller and smaller and smaller, so are my y values. They're going to now down to negative infinity. As my x values are getting bigger and bigger and bigger, the y values are going up to positive infinity. So the limit as x goes to negative infinity of x cubed is negative infinity. And the limit as x goes to positive infinity of x cubed is positive infinity. And remember, on any limit problem, the first thing you want to try and do is plug in the value. So if I plugged in negative infinity into x to the third, I would have negative infinity times negative infinity times negative infinity, which would be negative infinity. And then negative x cubed, that's a reflection of x cubed, so it's going to look like a snake going the opposite direction. So my limit as x's are getting smaller, so the limit as x approaches negative infinity of the opposite of x cubed, that's shooting up to the sky, so that would be positive infinity. And the limit as x goes to positive infinity of the opposite of x cubed is going to be negative infinity. Those are going down to the ground. So those are your basic polynomial end behaviors. And those are the most common ones that we talked about initially when we talk about end behavior. We can also talk about our rationals. So if we had like y equals 1 over x, that's our rational function. What's the end behavior of that guy? Well, this graph looks like this and like this. So what's the y value doing on this graph as my x values are getting really, really big or really, really small? Well, let's take a look. what's happening on this graph as my x values are getting smaller and smaller and smaller. So as x goes to negative infinity, my y values are getting smaller and smaller and smaller, or they're getting closer and closer to 0, sorry. So my limit as x goes to negative infinity of 1 over x would be 0. And what's happening as they're getting bigger and bigger and bigger? What's the limit as x goes to positive infinity of 1 over x? Well, those are also getting closer and closer to 0, those y values, so that limit would be 0. So your rational ones behave a little bit differently than the polynomial ones. And so remember, your first step in any limit problem is to plug in. So if I plugged in infinity, 1 divided by infinity, that'd be 1 divided by a really, really big number, is going to get closer and closer to 0. So let's remember our horizontal asymptote rules. So those are the rules that apply to our rational function. There's 3 of them. So remember, our first rule is what happens if the denominator wins. So the horizontal asymptote rules are the degree war game. So we're playing the degree war. Who wins, the numerator, denominator, or is it a tie? So we could have something like f of x equals x squared minus 4 over x to the 5th plus 3x minus 2. So who wins the degree war? Well, x to the 5th is the biggest degree, so when the denominator wins, your horizontal asymptote is always y equals 0. So that's option 1. You could have a tie. So this could be like f of x equals 3x minus 4 over 5 plus 2x. And notice they both have a degree of 1, 3x and 2x, so it's a tie. And when it's a tie, the horizontal asymptote is at the ratio of the leading coefficients. So in this case, the coefficients are 3 and 2. So the horizontal asymptote would occur at 3 over 2, or 1.5. Your last option is what happens if the numerator wins. Well, if the numerator wins, we could have something like f of x equals x squared minus 3 over x plus 1. The numerator has the bigger degree. And so what's happening is that there's none. There's no horizontal asymptotes because there's going to be a slant asymptote. The end behavior of the graph, so this is what's happening as x is going to infinity or x is going to negative infinity. Basically what we're doing on these problems is we're finding the end behavior. So if I took and plugged in x equals infinity into these problems, the numerator would win. I'd get infinity squared minus 3 over a smaller type of infinity plus 1. Since the numerator wins, it has a bigger, my answer to that would be infinity. So there's not going to be a horizontal asymptote because the graph is going to shoot up high into the sky and not level off at a given y value. So those are your horizontal asymptote rules. So my limits as x approaches infinity for these problems. So let's say we have the limit as x approaches infinity of 3x minus 2 over x squared plus 4. So again, if I took infinity and plugged it in, who wins? Well, in your mind, what's bigger, 3 times infinity or infinity times infinity? Infinity times infinity is going to win. So what's a small number divided by a really, really, really big number? That's going to be 0. So if the denominator wins, the limit as x goes to infinity or negative infinity is going to be 0. Or if we have the limit as x goes to negative infinity of 2x squared minus 5 over 4 plus 3x squared, who wins this time? Well, it's 2x squared over 3x squared. And so if I plugged in negative infinity in both of those, I would get a tie. So basically the infinities are going to cancel each other out, and all that's left is going to be 2 over 3. So the limit of rational functions as the x values go to infinity or negative infinity, you're just going to use the degree wars to find your answers. What if the numerator wins? So let's say we want the limit as x goes to infinity of 2x to the third minus 5 over x plus 1. Well, the numerator wins, but now we have to decide, is my answer going to be infinity or negative infinity? So number 3, we actually have to do a little bit of math other than just knowing the degree war game. So if I plugged in positive infinity, 2 times positive infinity times positive infinity times positive infinity is going to generate a positive number. And if I plug in positive infinity down here, that's going to generate a positive number. And a positive over a positive is positive. So since the numerator wins, my answer is either going to be infinity or negative infinity. And in this case, it'll be positive infinity. Well, let's look at that same problem. But this time, let's look at what happens if we plug in negative infinity, or almost the same problem. Let's say we have 3x squared minus 1 over x plus 5. So again, the numerator is going to win the degree war, So the answer is going to be infinity or negative infinity. We got to decide which one it is. So if I plug in negative infinity in for both of those x's, I'd get 3 times negative infinity, which would be a positive answer. And then I would get negative infinity plus 5 on the bottom, which would still be negative. So I have a positive over a negative, which is a negative. So in this case, it would be negative infinity. So that's how you could do limits as x approaches infinity for irrational functions. So you guys go ahead and see if you can pause your video and try these 4. So find each limit using the rules we just talked about. All right, so in the first one, we have x over x, so it's a tie. And when it's a tie, it's going to be the leading coefficients. So the limit of this would be 1, because again, x is going to infinity. This only works when x is going to infinity or negative infinity. On our next one, again, x is going to infinity. The denominator wins the degree war, and when the denominator wins, the limit is automatically going to be 0. The next one, the limit is x goes to infinity, and then we have 3x squared over 4x squared, so it's a tie. So it's going to be the ratio of the leading coefficients, so it'll be 3/4. On the next one, the denominator wins, and when the denominator wins, again, your x is going to infinity, so when the denominator wins, it'll be 0. All right, same thing. Go ahead and pause the video and try these 4. All right, on the first one, the denominator wins, and when the denominator wins, as x is going to infinity or negative infinity, the limit will be 0. On the one below it, it's a tie. We have 8x to the second over 2x to the second, and when it's a tie, it's a ratio of the leading coefficients, so it'll be 4. Again, this is the limit as x is going to an infinity. On the next one, I have the limit as x goes to negative infinity of 4 plus 3 over x. You've got 2 options. If you remember your limit properties, you could break this up into 2 limits. The limit of x as x goes to negative infinity of 4 plus the limit as x goes to negative infinity of 3 over x. You could split it up into 2 limits. And remember, the limit of a constant is always just going to be the constant itself, so that'll be 4. And then in the second piece, the denominator wins. And when the denominator wins, as you're going to infinity or negative infinity, the limit would be 0. So this is just going to be an overall limit of 4. You could also have gotten a common denominator, so times by x times by x. And this would be the limit as x goes to negative infinity of 4x plus 3 over x. And since it's a tie, it's the ratio of the leading coefficients would also be 4. So you could do it either way. You could split it up or get a common denominator. So on the next one, I'm going to split it up. So this would be the limit as x goes to infinity of 10 minus the limit as x goes to infinity of 2 over x squared. The first one's limit is 10. In the second one, the denominator wins, so its limit is 0. So 10 minus 0 is 10. So the overall limit for that problem would be 10. Vertical asymptote rules. So we talked about horizontal asymptotes. When does a function have a vertical asymptote? So when would f of x over x plus 3 over x squared minus 4 have vertical asymptotes? So vertical asymptotes occur, if you guys remember, when the denominator equals 0 and it's not a whole. And wholes occur when things cancel from the numerator and denominator. So a vertical asymptote occurs when the denominator is equal to 0. So when does x squared minus 4 equal 0? That occurs when x is equal to 2 or x is equal to negative 2. So this graph would have vertical asymptotes at negative 2 and positive 2. Which means what's happening on the graph as x goes to 2. So we want to know what's the limit as x goes to 2 of x plus 3 over x squared minus 4. Well, if I plug in 2, I would get 5 over 0. That's not an indeterminate form. That's undefined. When this happens, that means the limit's either going to be infinity or negative infinity, and we've got to figure out which it is. So what we do is we look at the limit as I approach x from both sides. So what's happening as I'm approaching on the left-hand side of 2? So what we can do is we can either graph it and see what's happening, or we pick a number that's a little bit on the left-hand side of 2. So I could pick like 1.99. And if I picked 1.99, is my value that I get going to be positive or negative? So if I try that, that would be x plus 3 over x squared minus 4. So if I took 1.99 and plugged it in for both of these, 1.999 plus 3 would give me positive numbers. 1.99 times 1.99 minus 4, well, that's going to be a negative because the 1.99 squared is going to be smaller than 4. And a positive over a negative is a negative, so this answer is going to be negative infinity. So remember, when you're dividing by a number really, really close to 0, like 5 divided by 0.00000001, it's actually going to generate a really, really big number. And so that would be like 5 million or 5 billion. So it's approaching infinity, but in this case, since it's a positive over a negative, when I plug in a number a little bit smaller than 2, it would be negative infinity. So what's happening as I approach 2 on the right-hand side of x plus 3 over x squared minus 4? So a number a little bit bigger than 2 could be 2.01. So if I took 2.01 and plugged it into the numerator and the denominator, if I plug it into the numerator, I'd get a positive. And then if I plug it into the denominator, 2.01 squared is bigger than 4. So if I subtract them, I would get a positive. So this is going to be positive infinity. And so at vertical asymptotes on the graph, if you try and find the limit at your vertical asymptotes, the limit is either going to be infinity or negative infinity. So let's pull this graph up on Desmos and see what it looks like. So let me get rid of these guys. And so I'm going to put it in parentheses because the numerator has multiple terms. So x plus 3 and then divided by x squared minus 4. So if I graph this, so notice at 2 and negative 2, we've got asymptotes. And so we just looked at what's happening as I'm approaching 2 from the left and the right. So 2, if I'm approaching on the left-hand side of 2, the graph is shooting down. And if I approach on the right-hand side of 2, the graph is shooting up. So notice that means that the limit as x goes to 2 from the left would be negative infinity, as x goes to 2 from the right would be positive infinity. So let's go ahead and find some vertical asymptotes. So if I wanted to find the vertical asymptote for the first one, the first thing, remember, it's when the denominator equals 0 and it's not a whole. So I'm going to factor out 3. And then if I factor this, I would get x plus 3x minus 2. And so where does the denominator equal 0? Well, it equals 0 at negative 3 and 2, so those would be the vertical asymptotes for that graph. For the next one, where does the denominator equal 0? It would equal 0 at x equals 4, so those would be the vertical asymptotes for that graph. So you guys go ahead and find the vertical asymptotes of the bottom two, and you can check your work against the finished notes in Desmos, or sorry, the finished notes from class today. All right. Now let's look at these as we're approaching these on the left and the right-hand side of 0. So we have the cosine of x squared minus x over x squared. Well, if I try and plug in 0 into this, the cosine of 0 is 1, and 1 over 0 squared, so I would get 1 over 0, which again is sad. So my answers are going to be infinity or negative infinity, because if I'm dividing by a number really close to 0, it actually makes it a really big number when you actually divide it out. So let's figure out what's the limit as x goes to 0 from the left-hand side of cosine of x squared minus x over x squared. So I could do like negative 0.001. And so if I plug that in, the denominator would be positive, and then the cosine would be positive as well, because I think we're just a little bit in the fourth quadrant. And so I believe that'd be positive infinity. But again, we can check by looking at Desmos. And if we graph this, so we have cosine of x squared minus x, and then divided by x squared. And we're wondering what's happening as I'm getting closer and closer to 0. Oh, I did x2, not x squared. I was like, why isn't it graphing? There we go. So as I'm getting closer and closer to 0, notice what's happening on the graph. On both sides, it looks like it's shooting up towards infinity, so we did that right. So the limit as x goes to 0 on the right-hand side of cosine of x squared minus x over x squared would also be positive infinity, or you could plug in an answer a little bit bigger than 0, so like 0.01, to see what happens. All right, so you guys go ahead and think through the next three, either using Desmos or the idea of using a number a little bit bigger or smaller than 1, or a little bit bigger or smaller than pi or 2, and you guys can check your work against the finished notes from class today. So we talked about the squeeze theorem a couple classes ago. And so remember, your squeeze theorem is telling you if something can be squeezed between two numbers, you might be able to find the limit of an expression involving that if you couldn't find the limit initially. So if I look at this, what's the limit as x goes to negative infinity of this? Well, if I plug in negative infinity, the denominator would be infinity. And if I plug in negative infinity into cosine, well, cosine fluctuates in between 1 and negative 1. So I can't necessarily tell what the limit is going to be because I don't know what the numerator would be, because cosine's fluctuating in between negative 1 and positive 1. So I can't exactly tell what that value is going to be exactly as I go to negative infinity because it keeps changing. So what we're going to do is we're going to go back to that idea. Do you remember what cosine and sine always have to be squeezed between? They get to be squeezed in between negative 1 and 1. So since that's a true statement, the graph of cosine is always between negative 1 and 1. Let's see if we can rewrite that as this expression by adding, subtracting, and dividing and see what we get. So since I want negative cosine, I'm going to multiply every term in here by negative 1. So that's going to change that to positive 1, and all the signs are going to flip. And then this would be negative cosine, and then this would be negative 1. I'm going to write it the other way because I like looking at it like that way better. And now I have this expression. So now I have the negative cosine. I need that 1 in front, so now I'm going to add 1 to each piece. And we're just using the addition property of equality and the multiplication property of equality, so we're still good. So now I have 0 is less than or equal to 1 minus cosine x, which is less than or equal to 2. And now I'm going to divide everybody by x squared to get that x squared. So divide by x squared, divide by x squared, divide by x squared. So now 0 divided by x squared is still 0. So 0 is less than or equal to 1 minus cosine x over x squared, which is less than or equal to 2 over x squared. And now let's add in our limit piece that was at the beginning of the problem. So the limit is x goes to negative infinity. The limit is x goes to negative infinity. And the limit is x goes to negative infinity. Well, the limit of any constant is just the constant itself, so that's going to be 0. The middle piece was the piece we didn't know, so that's the limit as x goes to negative infinity of 1 minus cosine x over x squared, which is going to be less than or equal to the limit as x goes to negative infinity of 2 over x squared. Well, that's a degree war game, and since the denominator wins, the limit's going to be 0. So notice, since that expression is sandwiched in between 0 and 0, then this limit, overall limit, has to be 0 by the squeeze theorem. All right, you guys go ahead and do the exact same thing using the squeeze theorem with the sine of x squared. Remember, the sine of anything has to be sandwiched in between 1 and negative 1. So that would be your first step. So see if you can go through the process like we just did and tell me what the answer would be. You can check your work against the finished notes from class today. All right, what if we're going to go backwards? What if you know what all the limits are, what all the heights of the graph should be at different x points, but they didn't give you the picture and they want you to graph the picture? Well, is there only one right picture? No, there's going to be an infinite number of pictures that will work. But when you're done, it has to be a function. What does it mean to be a function? Well, that means it has to pass the vertical line test, meaning that every x is only going to have one y partner. So when you're done, if it doesn't pass the vertical line test, then you connected some pieces wrong, and you're going to have to redraw it. So let's go through this. We have the limit as x goes to 2 is negative 1. So that means as I'm getting closer and closer to an x value of 2 on the graph, the height of the graph is getting closer and closer to negative 1. So I'm just going to make the point 2, negative 1 be a point on the graph. And remember, a limit can't be an isolated point, so it has to be connected on both sides. But I don't know what it looks like, so I'm just going to make it kind of look like a parabola. I might have to erase that later based on other pieces, but for right now, I'm just going to make it look like that. So now if you were to look at this graph, what is the limit as x goes to 2 of what I just drew? Well, the limit as x goes to 2 is negative 1, because that's going to be the height of the graph there. All right, let's do the next one. The limit as x goes to 4 from the right-hand side is negative infinity. So as I'm getting closer and closer to 4 on the right-hand side of my graph is shooting down to negative infinity. So as I'm getting closer and closer to 4, all of a sudden my graph is going to shoot down to negative infinity. That means that there's going to be a vertical asymptote on the graph right there. Remember, that's the way that a graph would shoot up or down in the middle of the graph, is if you had a vertical asymptote. So I'm just going to make it look like that. I don't know what's happening further to the left on the graph, so I'm just going to leave it for now and see if something else happens. All right, my next piece is saying as x is getting closer and closer to 4 on the left-hand side, that piece is shooting up to positive infinity. Well, it looks like the pink piece that I drew for the first part of the graph is going to be connected to this piece. And so as I'm getting closer and closer to 4 from the right, this is just going to keep shooting up to positive infinity. So I connected it to my pink piece. Now let's look at our next piece. This is saying as x is getting closer and closer to positive infinity. So that's on the right side of the graph, so the right end behavior. What's my graph doing? It's saying that it's shooting up to positive infinity. So the right-hand side of my graph is going to be connected to this blue piece, and this is saying that the end behavior is positive infinity, so I'm just going to draw it so it's eventually shooting up to the sky to positive infinity. And now the next piece of my graph is saying that as x is getting closer and closer to negative infinity, so that's the left end behavior, what's it doing on the left-hand side of my graph? It's saying that it's leveling off at a height of 2. That would be like a horizontal asymptote. So I'm going to connect it to my pink piece because that's the farthest to the left that I have so far. And now I'm just going to draw this graph so it levels off at a height of 2. At the end, you should be able to look at your picture and say what the limit is at all of the pieces and have it make sense. So on this picture, if I approach 4 from the right, is the limit negative infinity? Yes. If I approach 4 from the left, is the limit positive infinity? Yes. As I'm getting closer and closer to the right side of my graph, as x goes to infinity, is the limit positive infinity? Yes. As I'm going to the left-hand side of my graph, as x goes to negative infinity, is the limit 2? Is the height of the graph 2? Yes. So it looks like we did this right. All right, you guys go ahead and pause your video and see if you can do this one. All right, so if we were to graph this, again, I'm just going to do it in pieces with different colors. If I were to graph the limit as x goes to negative 2 from the right-hand side, so I'm just going to go, here's negative 2. On the right-hand side, it looks like it's leveling off at 2. So that means that on the right-hand side of 2, it looks like it's at a height of 2. So I'm just going to put an open circle here, and then I don't know what's happening, so I'm going to connect. But it's only happening as I'm approaching negative 2 from the right, so I'm just going to do that. And now I'm going to do another piece. I'm going to do negative 2 from the left, so the one right underneath it. It's saying as I'm approaching negative 2 from the left-hand side, that's at a height of negative 1. So here's a height of negative 1. I'm just going to do an open circle. And then this is coming from the left-hand side. I don't know what's happening, but I'm just going to draw a little curvy-looking line over there. And that would be the height as I'm approaching negative 2 from the left-hand side. Could both of those circles be filled in and still have it be a function? No, because it wouldn't pass the vertical line test. Could I fill in one of the circles and have it be true? Like, could I fill in the circle here and have it be true? Yes. So they both could be open, or one of them could be closed to have this still be a function. All right, let's keep going. My limit as x is getting closer and closer to positive 4. So 1, 2, 3, 4 is 3. So that means from both directions, the graph of my function at 4 is at a height of 3. I don't know what's happening on either side, so I'm just going to make this a sad-looking parabola on both sides. Now it's saying that my function, as the x values are getting closer and closer to 1, that the limit's infinity. So as I'm getting closer and closer to 1, both sides are shooting up to infinity. So remember, if in the middle of the graph it's shooting it up to infinity or down to negative infinity, that means that I have a vertical asymptote. So that means on the left-hand side, I'm going to connect it to the pink one. It's going to shoot up to positive infinity. And then on the right-hand side, I'm going to connect it to the blue one, and this one's also shooting up to positive infinity. So as my graph is getting closer and closer to 1, on both sides it's shooting up to positive infinity. And now we've just got some random isolated points. It's telling you that f at negative 2 is equal to negative 1. So I happen to fill in the right circle. So f at negative 2 is at a height of negative 1. So that should have been my closed circle. And then it's telling me that f at 4, so my function value at 4 is positive 1. That means that I have to fill in a solid point right there. What does that mean about the blue dot above it? that means that that should not have been a closed dot. It needs to be an open dot so that the limit exists, and the limit as x goes to 4 is at a height of 3, but that it's not actually the function value there. It's not actually the closed circle there. All right, so that's it. Those are the only pieces left, and they didn't tell me about anything about the end behavior. So that means that I could either finish the function there, or I could give it tails, and just those tails could indicate that it's going anywhere you want it to go. But then remember at the end, if you went back through, all of those limits should be true if you just looked at them based on your graph.